Hello and welcome to another episode of our series NASA Biology on Earth and in Space. Most scientists agree that for life to exist on a planet, there must be an atmosphere. But what kind of atmosphere will allow life to develop? By studying Earth's atmosphere, scientists hope to find an answer. In this show, Dr. Joel Levine of the NASA Langley Research Center tells of the research being done to understand our own atmosphere.
The atmosphere is composed of several hundred gases. Most of the gases in the atmosphere we refer to as trace gases. They're gases in very low concentration. But let's talk about the major gases first. The major gases in the Earth's atmosphere are molecular nitrogen, N2. About 78% by volume of the atmosphere is molecular nitrogen. Second most abundant gas is molecular oxygen, about 21%. The third most abundant gas in the atmosphere is argon. Argon is a heavy inert gas that results from the radiogenic decay of potassium-40 in the Earth's crust. And argon-40 is produced from the decay of potassium-40. Those are the three major gases in the Earth's atmosphere, the three major permanent gases. Water vapor is present in the atmosphere in variable amounts, from a fraction of a percent to several percent, depending on the season, the location, and so on. Now, in addition to those four gases, and if you add them up, they're probably 99.99% of the total volume of the atmosphere, there are several hundred trace gases. Things like carbon dioxide. Carbon dioxide is about 0.03%. There are nitrogen oxides, carbon monoxide, ozone, and the list just continues. One of the interesting things is to try to assess how these trace gases are varying in the atmosphere. We have reason to believe that different man-made activities, combustion, internal engines, burning of fossil fuels, are increasing the trace gas content of the atmosphere. But as far as the bulk composition goes, nitrogen, oxygen, argon, water vapor. The atmosphere surrounding the Earth, the gaseous envelope surrounding the Earth, has been in place for about 4.5 billion years. The Earth, the other planets, the Sun, are all about 4.5 billion years old. We have reason to believe that the atmosphere around the Earth formed at about the time the Earth formed, 4.5 billion years. Over geological time, over that 4.5 billion years, the composition of the atmosphere has changed tremendously. For most of the first 4.5 billion years, the composition of the atmosphere was controlled by several different processes. First, volcanism. The atmosphere originally was in the interior of the Earth, and it was released during a period of great volcanic activity in the early history of the Earth. In addition to volcanism, atmospheric reactions, chemical and photochemical reactions in the atmosphere transform one gas to another through chemical processes. And finally, biology. The presence of living systems at the surface of the Earth has modified the composition of the atmosphere over geological time. For example, oxygen. The oxygen in the atmosphere, the second most abundant gas, 21% by volume, has resulted from photosynthetic activity in green plants. The green plants produce oxygen as a byproduct during the process of forming carbohydrates for food. So, over geological time, the atmosphere has resulted from a combination of these different processes. About 100 years ago or 150 years ago, a new source of gases was added to our inventory of atmospheric gases, and that's industrialized society. And by industrialized society, I mean the production of trace gases by burning of fossil fuels, particularly coal, through internal combustion engines such as we have in our automobiles. So the atmosphere has changed over geological time as a natural response to different changes in the environment. Over the last 100 or 150 years, anthropogenic activities, man-made activities, are also changing the composition of the atmosphere. For many years, perhaps 40 or 50 years, it was believed that the Earth's primitive or paleoatmosphere was composed primarily of methane, ammonia, and molecular hydrogen. And in fact, it was believed that this atmosphere was the atmosphere that, energized by lightning and/or ultraviolet radiation, form the first amino acids, the building blocks of life. About 3 or 4 years ago, we took a very hard look at the whole question of an ammonia methane atmosphere in the early history of the Earth. And we came to a very interesting conclusion. We came to a conclusion that the photochemical lifetime, the lifetime of methane and ammonia against different atmospheric reactions, was so short that methane and ammonia couldn't have been around more than 100 years on Earth. Now, ammonia and methane are destroyed very efficiently in the early history of the Earth's atmosphere, and there are no sources to produce new methane and ammonia. The methane and ammonia produced in the atmosphere today result from biological activity, from microorganisms in soil. Metabolically, they produce methane and ammonia. But this is a period in the Earth's history prior to life, and so clearly life couldn't have been the source of methane and ammonia in the Earth's early history. Yet some relatively simple computer calculations, computer modeling that we did, suggested that methane and ammonia were so short-lived that they couldn't have been around in the early atmosphere for any appreciable amount of time. And instead, we believe that the early atmosphere consisted of carbon dioxide, nitrogen, and water vapor, instead of methane, ammonia, and molecular hydrogen. And recent experiments dealing with chemical evolution is the formation of complex organic molecules from simple atmospheric gases. If you take a mixture of CO2, water vapor, nitrogen, expose it to lightning in the laboratory or ultraviolet radiation, you can form the complex organic molecules, the amino acids, the precursors of living systems. In the early 50s, it was shown that if you take mixtures of methane, ammonia, and hydrogen, you can form amino acids. And within the last 2 or 3 years, it's been shown that if you take mixtures without methane and ammonia, CO2, nitrogen, and water vapor, you form the same organics. The first complex organic molecules on the surface of the Earth, the precursors of living systems, were formed from atmospheric gases. Gases in the atmosphere were acted upon by atmospheric lightning and solar ultraviolet radiation, and the simple atmospheric gases were synthesized into more complex organic molecules such as amino acids. So from the very beginning, in the early history of the Earth, the atmosphere was very important in the evolution of life. And since life has formed on Earth and evolved, the atmosphere is very important in protecting it. The sun gives off electromagnetic radiation all across the spectrum: X-rays, ultraviolet, visible, infrared, and radio. And ultraviolet radiation between 2,000 and 3,000 angstroms, is very lethal to biological systems. If we were exposed, if living systems were exposed to ultraviolet radiation, life on Earth wouldn't continue. It's biologically very damaging. Fortunately, we have a trace gas in the atmosphere called ozone, an allotropic form of oxygen, symbol O3, and ozone has the unique property of absorbing ultraviolet radiation and hence shielding the surface of the Earth from this dangerous radiation. So not only did life really originate via atmospheric gases in the early history, but now ozone in the atmosphere protects life at the Earth's surface from ultraviolet radiation. We divide the Earth's atmosphere into several spheres. The first sphere is called the troposphere. That goes from the surface to about 10 or 12 kilometers above the surface. Above the troposphere is a region known as the stratosphere that goes from about 12 kilometers to about 50 kilometers. Above the stratosphere, we have the mesosphere that goes to about 80 kilometers. Above 80 kilometers, we have the region known as the thermosphere, and the thermosphere continues from about 80 kilometers up to about 500 kilometers, where we have the exosphere. Now, superimposed on that structure are two other regions. The first is the ionosphere. The ionosphere are several regions in the Earth's atmosphere where we don't have neutral molecules, but we have electrons and ions, positively charged atoms. And the ionosphere begins at about 50 kilometers and goes up to several hundred kilometers. There's another region of charged particles in the Earth's atmosphere. That's called the magnetosphere, which includes the Van Allen radiation belts. And we have protons and electrons, to a large extent of solar origin. These are solar particles that are trapped in the Earth's magnetic field in the magnetosphere. So we do define the Earth's atmosphere in different spheres. The troposphere is where our weather takes place. All of the water vapor, not all, 99% of the water vapor in the atmosphere is contained in the troposphere. We have clouds, we have precipitation. Right above the troposphere, the stratosphere, the important thing about the stratosphere is that's where the ozone is located. 90% of the ozone in the atmosphere is located in the stratosphere. The troposphere and stratosphere account for about 99% of the total mass of the atmosphere. Even though the atmosphere extends up to several hundred kilometers, 99% of the mass, more than 99%, falls within the troposphere and stratosphere. The troposphere has about 85% of the total mass of the atmosphere. The stratosphere has about 14%. To make measurements of atmospheric gases, atmospheric composition, there are several different techniques. You can make measurements from the ground, from aircraft, and now we're just beginning to make measurements from space. Most of the space measurements of atmospheric gases are based on remote sensing. That is, certain gases absorb and re-emit radiation at certain wavelengths. And by using infrared, microwave, ultraviolet wavelengths, you can actually see the spectral signature of different gases. Now, from aircraft, we have LiDAR systems, where a LiDAR is a laser system that sends out a beam of light, and you can tune the wavelength, and when you tune the wavelength, you can measure the backscattered radiation, and you can study atmospheric gases that way. We call that an active technique because we're actually transmitting a signal. And then at the ground, which is the easiest place to make the measurements, there are mass spectrometers, gas chromatographs, laboratory techniques, and so on. So chemically, you can do analysis at the ground. So there are a whole range of ways to make measurements of atmospheric gases. One of the exciting developments in the last decade has been the application of computer numerical models to study the atmosphere. When we talk about computer numerical models, we're talking about different type models. For example, we have models that study and predict atmospheric wind motion and pressure changes, the global circulation of the model. We also have models that predict chemical changes. We have models, which are called photochemical models, that try to predict how the atmospheric composition has been over geological time and where it's going to be in the future. And these are chemical models. We also have what we call climate models, models that take into account clouds and ocean temperature and circulation of the atmosphere and try to predict what the future climate of the Earth will be. So one of the real exciting advances in the last decade has been the application of computer techniques and numerical techniques to study the atmosphere. And there's some very exciting results with computerized modeling of the atmosphere. The computer models of the atmosphere, the so-called photochemical models of the atmosphere, are models that include our understanding of the physics and chemistry of planetary atmospheres. What we do is we put into the model the different processes that are operational in planetary atmospheres. For example, our model for the Earth's early atmosphere includes about 100 different atmospheric gases and about 600 atmospheric reactions. These atmospheric reactions are initiated by solar photons, light energy from the sun, that break down gases like CO2, carbon dioxide, and water vapor into its constituent atoms, such as carbon monoxide, oxygen, hydrogen, and so on. And then we trace what happens, the chemical reactions resulting from these photochemical reactions. And we keep track of the production of gases and the destruction of gases. We have vertical motions to simulate vertical winds in the atmosphere. We have precipitation. to wash out water-soluble gases. We have the solar radiation coming in, and we know that the radiation from the sun has varied over geological time. The sun has gotten brighter. We consider that. Atmospheric chemical reactions are temperature dependent, so we calculate the temperature of the Earth's surface and the Earth's atmosphere as we do our calculation. And it's a time-dependent model. We start 4.5 billion years ago, and we do the calculation increments of several thousand years until we converge or reach the final, the atmosphere today. We have photosynthetic production of oxygen. We have carbonate rocks being formed. All of the known processes, geological, geophysical, and atmospherical, as well as biological processes, are put in the computer model. And we're talking about a computer model that took 5 or 6 people, 5 or 6 years to develop. The Earth's atmosphere is the only atmosphere in the solar system that has large amounts of free oxygen. So the oxygen resulted from photosynthetic activity. This was very important for 2 reasons. The evolution of oxygen in the Earth's atmosphere was important for 2 reasons. The first is it opened up the metabolic path of respiration by which living systems could burn food and get energy. Prior to respiration, biological systems, in the absence of oxygen, used fermentation to get energy. And respiration, which evolved once oxygen evolved in the atmosphere, is a much more efficient way for a living system to make energy. So from that point of view, it was important, an important biological milestone. But another equally important biological milestone is that once oxygen reached a certain point, ozone was formed photochemically from oxygen. Our computer calculations suggest that once oxygen reached 1/10 of its present atmospheric level, there was sufficient oxygen in the atmosphere to form ozone. And once you formed ozone in the atmosphere, ultraviolet radiation, for the first time in the history of the Earth, was shielded from the Earth's surface. And the living organisms, which we think evolved in the ocean, could go on land for the first time in history. Prior to the evolution of the ozone layer in the atmosphere, life was confined to the ocean because several meters of ocean offers protection that the ozone in the present atmosphere offers. In the early 70s, 1971, 1972, we realized really for the first time that several man-made activities or man-made emissions of gases potentially can impact ozone and perhaps lead to the inadvertent depletion of ozone in the upper atmosphere. If you decrease ozone in the upper atmosphere, you would tend to increase the amount of ultraviolet radiation reaching the surface of the Earth. This isn't good. The first indication that we had that there are man-made gases that may impact ozone in the upper atmosphere had to do with the supersonic transport. In the early 70s, we were considering, the United States was considering a prototype SST, and in 1971, a chemist at the University of California, Berkeley, Harold Johnston, published a paper in Science magazine suggesting that exhaust gases composed of nitrogen oxides may lead to the destruction of ozone in the upper atmosphere. By nitrogen oxides, we mean 2 compounds in particular, 2 gases. The first is nitric oxide, which has a symbol NO, and also nitrogen dioxide, NO2. What Harold Johnston pointed out was that there are chemical reactions involving ozone and the oxides of nitrogen that may lead to the destruction of ozone or depletion of ozone in the upper atmosphere. Right after the SST, atmospheric chemists began looking at chlorofluoromethanes. Chlorofluoromethanes are man-made molecules that were used in aerosol spray cans to propel the material out of the spray can, deodorant or paint, whatever you wanted. Well, it was pointed out that these chemically inert chlorofluoromethanes diffuse to the upper atmosphere, the stratosphere, and in the stratosphere, solar radiation breaks down the molecule, releases chlorine. Chlorine destroys ozone very rapidly. So that was the second scare about ozone depletion. So within the last 15 or 20 years, we have investigated the possibility of the inadvertent depletion of ozone in the upper atmosphere by man-made gases. This is a problem of great concern not only in the United States, but all throughout the world. The World Meteorological Organization, WMO, has conducted extensive studies and workshops. The United States National Academy of Science, NASA, the National Science Foundation, all these agencies have looked at the problem. I think there are several reasons that NASA is interested in studying the Earth's atmosphere. I guess the thing that comes to mind first is to study the atmosphere, you really need the global perspective. And NASA, by virtue of its satellite program, does in fact have the global perspective to look at the Earth on time scales and distance scales that are of importance. In addition, NASA's involved in a very active program of planetary exploration. We're studying the atmospheres of the other planets, and we've learned a lot about our own atmosphere in the process. But there are more immediate or more urgent reasons to study the atmosphere. In the early 70s, when we became aware of the fact that different man-made gases may impact the ozone layer, NASA was officially given the charter by Congress in the mid-70s to assess the ozone problem, to see if it's a problem, to begin detailed theoretical studies, satellite programs, measurement work, and so on. So NASA's charter was expanded to include the effect of man-made gases and man-made activities on stratospheric ozone, and NASA's been doing what it was directed to do. But the study of planetary atmospheres is truly a global problem to study. And by virtue of the satellite program, advanced technology and remote sensing, and different measurement techniques, and a very active program of planetary exploration, NASA is the logical agency to study this. The Upper Atmospheric Research Satellite, UARS, will study the region of the atmosphere known as the stratosphere, the region where 90% of the ozone is found. UARS will study the stratosphere and the region above the stratosphere called the mesosphere. Now, one of the key objectives of this whole program, the UARS program, is to better quantify ozone, the concentration, the variability, how it varies with latitude, how it varies with season, how it varies with level of solar activity. So one of the prime objectives is to study ozone, but it'll also make measurements of the other gases that affect ozone's concentration, such as the oxides of nitrogen and methane and water vapor. We'll measure temperature. It'll be a very comprehensive experiment to study the Earth's upper atmosphere, primarily centered around ozone. I think that a major milestone in our understanding of the Earth's atmosphere will come about in the 1990s with the development of the space station. I think that once we have permanent habitation in space, once we have astronauts looking at the Earth from a permanent platform, we're going to greatly enhance our understanding of the atmosphere, of the weather, of atmospheric composition, of climate, in fact, of all the Earth sciences. And I think that will be a major milestone in our understanding of the atmosphere. I think once we have the space station, that trips to the other planets will be much easier. It will be much easier to visit Mars and Venus and the other planets from space station because you don't need the tremendous thrust required that you do to visit these planets from the surface of the Earth. And I think that in general, scientists haven't been very enthusiastic about the space station. They haven't been as enthusiastic as they should be. I think it's going to offer a unique opportunity to study our planet and the atmospheres of the other planets and the other planets themselves. And I think that we really have to begin thinking as scientists about how to maximize the scientific return from the space station. A lot of scientists are concerned that the funding required for the space station will affect their own research programs. I think that's a short-sighted concern. I think the long range, it's going to open up new vistas for all science from space. I think we have to think about how to utilize this new facility in space, and I think it's going to be a major boom to our understanding of the Earth, its atmosphere, and the other planets.
During the past 200 years, there has been an explosion of scientific information. Human beings are no longer content to know that nature works. We want to understand how it works. Someday we may be able to answer the Earth's most complicated mysteries. Please join us next time when Dr. James Casting discusses the carbon dioxide cycle and how it affects the Earth. Until then, this is Lynn Bondurant saying goodbye from the NASA Lewis Research Center in Cleveland, Ohio.